Hi. All right, so now we're going to talk about the laws of thermodynamics collectively so we can get to entropy. Entropy is the goal in this chapter. So we've talked about first law, U is equal to Q plus W. And most of you have probably tried to use Q plus W to solve some of your problems and you can't go anywhere. The reason is because we don't know the functions of what Q and W follow. We know the equations of state that follow the rules of state functions, but if they're not state functions, we have no clue what's going on. So we got to get everything in terms of state functions, and that's where entropy is going to come in. Sorry. Okay. So first law, heat is conserved, or sorry, energy is conserved. First law, energy is conserved. So when heat is taken into account, I should say that. So the work and the heat collectively, we can identify where all the energy has to go somewhere. Okay, that's first law. What about zeroth, second, and third? So let's go take a quick field trip to talk about the zeroth law. Hi. Okay, I'm standing in my hallway. This is upstairs, and outside, you probably can't see it because of the glare, is winter. I will give you an up close and personal look. Yay! There's Richard Santarib's house. Go team. He lives across the street from me. He's a math professor who retired last year. Anyway, okay, so I'm on the second floor of a drafty house, pretty old. And so these windows, there's lots of condensation on these windows. Why is there condensation, you might ask? Well, because it's hotter in here and it's colder out there, and there's phase transition, and the water vapor is condensing on the windows because of the temperature differential. But why? I stick my hand here. I'm hot. It's cold outside. Which way does the heat flow? Pause. Sorry, that was the cat. So I have my hand here. Which way does the heat flow? Okay, heat is naturally going to flow one direction, not two. And that's the uniqueness of the zeroth law of thermodynamics. Heat is going to flow one way preferentially. And so if I put my hand here, I know that the window is cold, not because I feel that it's cold, but because there's a temperature differential. Heat is leaving my hand and going outside, or actually it's going to the window that's then carrying the heat outside, because heat flows from hot to cold. It does not flow from cold to hot. That would take thermal energy out of the cold and bring it in here. Think about what that would mean. If you had heat energy, any heat energy that exists outside right now, which it doesn't because it's freaking cold outside, any heat energy that comes in is going to originate from somewhere. Well, you can't bring it in from the cold because there's no heat out there. There's heat in here, and heat is leaving and going that way. And so that's the zeroth law of thermodynamics. And actually, it's a way that we define temperature. And a lot of times you've probably heard the zeroth law as if product A or item A is in thermal equilibrium with item B, and item B is in thermal equilibrium with item C, then A and C are in thermal equilibrium from each other or with each other. That's stupid. I mean, it's true, but that is only telling you that if they're not in thermal equilibrium with each other, heat's got to go somewhere. And it's not a functioning definition of the zeroth law of thermo because it doesn't tell you much if they're already in equilibrium. We care about what happens when they're not in equilibrium and how they get there. So me and the window, not in thermal equilibrium. I put my hand against the window, heat will continue to flow until we are in thermal equilibrium. And lucky for us, well, I guess unlucky for us, it's cold as hell outside. And so we will never reach thermal equilibrium. I will continue to feel that the window is cold because heat will continue to flow from me to the window. Cool? Awesome. And in case you're curious, that's my ode to Tom Petty right there. It's in my stairwell. Yay, there's the stairs. Cool. Okay, back to thermo. Okay, so zeroth law, heat flows from hot to cold. First law, energy is conserved. Well, what about the second law? Okay, so if there's a hot body and a cold body, or a hot source or a hot reservoir and a cold reservoir, so this is thermal energy being stored and what we call a heat sink. Okay, so if there's a hot and a cold difference, what defines temperature, and actually I didn't mention the importance of the zeroth law of thermodynamics, is it gives us a definition of temperature. Temperature means heat is flowing, and you have a difference in temperature. Two things in equilibrium, they're going to be at the same temperature. Two things not in equilibrium, heat's flowing, you have a difference in temperature. So first law says that any energy that leaves the hot has to go somewhere, and we should be able to track it or account for it. Zeroth law says it's gonna go this way. So we know that Q is gonna go that way. Heat's gonna flow spontaneously. There's nothing we can do about it. Hot, cold, heat's gonna flow. But there is a possibility that we could convert this Q. Let's see if I can do this. Into work. Wouldn't that be great? Because Q plus W equals work. So any heat that's flowing, is there a possibility that we could take some of it and redirect it? Notice how I made the little arrow smaller, and redirect it into work. Well, that would be great, because then we can convert this naturally, spontaneously flowing heat into something useful, work energy. This is called an engine. Okay, but there's a kicker here, or there's a catch. So we can't, so the second law of thermodynamics says that, let me write it down. Okay, so the Kelvin-Planck statement of the second law: no process is possible in which the sole result is the absorbance of heat from a reservoir and its complete conversion into work. So what the second law says is there is no possible process in which all of the heat that's spontaneously flowing from the hot to the cold can be completely converted into work. Not possible. A lot of it can, but there's going to be some amount, Q, that has to be converted or not be converted into work. And this accounting of, if you don't convert 100% into work, what small percentage don't you convert? And actually, it's like the best engines are honestly like 33% efficient in terms of these heat engines. So 100% is ridiculous. But anyway, but there is always going to be some loss, and that loss is associated with entropy. Another definition of the entropy, of the second law of thermo, is that entropy of an isolated system increases in the course of a spontaneous change. Delta S total will always be greater than 0. So in the process of a spontaneous change, which the zeroth law says, if you have a hot body and a cold body connecting to each other, heat will spontaneously flow. Second law says there's no possible way that you can convert all of that heat energy into work. Some of it has to go to the total surroundings. So some of this Q cannot be converted into work, such that the entropy of an isolated system increases in the course of that spontaneous change. Now the entropy, and we'll get to this in a little bit, but I'm just going to quickly give you, ds is equal to dq reversible over T. And so at a constant temperature, the change in the entropy, this delta S, or this ds here, this in an infinitesimal change, is equal to dq. And so Q per temperature is related to that entropy. And so this small amount of Q that is lost will always be a positive value, such that this delta S will always be greater than 0 for a spontaneous change in an isolated system representing the total entropy. Now you can break up the entropy into the systems and the surroundings, so a delta S of surroundings and a delta S of the system, yielding a delta S of the universe, and so on. But this is the entropy increase that we're talking about. You can still have a decrease in entropy of the system or the surroundings, but the total entropy change will always be greater than 0 for a spontaneous process. And that can be related back to the Kelvin statement that says no complete conversion of heat into work can occur when you've got this natural flow occurring. The last thing I'll add is that a lot of folks will say that entropy is merely a measure of disorder in the system. Again, that's bullshit. It's not a measure of disorder. It's not related to chaos. Entropy is honestly related to a dispersal of energy. And so entropy will always favor, this is the second law, will always favor maximizing the number of states of energy that are occupied. It just so happens that that does mean that you'll have more states. You have more, quote, disorder, but it's inappropriate to say that entropy and order are related, because you can't quantify order and disorder. You can quantify, however, the number of possible states in a system. And so that's what we're going to, hopefully that's a good overview of entropy. And next video, we're going to dive into the Carnot cycle to really give a precise definition of what entropy is in terms of these processes. Go team.